Alright, so now we're going to start talking about designing for materials. Awesome. So, this is, as everything we do, very difficult, but also very important. And it's very important because everything depends on the material you make it out of, right? We don't make, well, that's a terrible example, but we don't make skyscrapers out of plastic, right? The choice of material describes what your part is capable of. It also limits how you will make it, which, manufacturing is a large component of the cost of your product, right? So material choice will not only affect the cost of your product through how much the material costs, but it'll also affect it through how you make it, right? As well as the lifetime of the product, if it fails too early and you have to replace it or not. And there's no better way to put this, but you're going to want to pick sexy materials like carbon fiber or titanium. Oops, that's not how you spell it. Titanium. Or tungsten, right? What's tungsten good for? It's dense and it's very good at high temperature applications. So these are all, you're going to want to pick exotic materials, right? That is not the point of this exercise. What is the point of everything we are talking about in this class? The point of everything in this class is to keep your eye on the bottom line, right? We want to pick the material that's going to satisfy the needs that we have. Period. I'll highlight that. A couple arrows. Alright. So why is this so difficult, though? Well, this is really difficult because we have a lot of conflicting requirements for our part, right? Very often we need lightweight, right? But we need it strong. We need it cheap. We need it corrosion resistant. Fatigue resistant. We need all of these things, and oftentimes it's very difficult to pick a material that has the right weight, strength, and is cheap enough, right? And that's always the thing. You can usually find a material that meets all of your requirements, but is it cheap enough? Are people willing to buy it? So you have to make compromises, right? Let's talk for a little bit about all of the things we have to worry about with materials. So many things, we're going to have to put a dotted line there just to make a new section. Alright, so just related to strength, right? Strength of a material isn't really that descriptive, right? We care about yield strength. Yield strength of a material. What stress causes it to fail, right? We care about ductility, right? After it's failed, does it just shatter or does it stretch, right? One big reason why cars will continue to be made out of metal for a long time is that metal is ductile, right? So when it does fail, it fails slowly. Like if you're in a crash, it'll crumple instead of just shattering into a million pieces. Fun fact, glass is many, many times stronger than steel, but we don't ever use it to make anything important because when it fails spectacularly, right? Young's modulus matters too, right? What does Young's modulus tell us? It tells us how much our part will deflect under load. It's one thing to be able to support an entire load without failing, right? It's another to be able to support it without deflecting so much that it's awkward, right? And hardness, right? Again, a material might support all the load that we ask it to. It might not deflect that much, but if it's under high wear conditions and it's not very hard, part might fail simply because you lose so much material. The part geometry changes and you're screwed. Or you scratch it and that causes a stress concentration. So hardness is important too. Beyond strength, right? We need to start worrying about how the material behaves over long periods of time, like fatigue. So I can spell this right. Fatigue. That looks weird. So, fatigue. What kind of loads will it have? How many cycles will it have? Type of load, right? You guys covered this in your design class, but type of load. Like, is there a different materials fatigue under different conditions, right? So if you have a strong base load with a small vibration, that's going to cause a different fatigue response than a large variation in load that is essentially varying around zero, right? And of course, the number of cycles that it can handle. Number of cycles. We have to worry about corrosion fatigue. Fatigue and so on. Let's put little scary squiggly lines around that. Fatigue. I hate fatigue. I mean, it's awesome, but it sucks. Fatigue. Oftentimes, right, what will kill a part first? Strength or fatigue? Fatigue will, right? You can stay well away from something's yield strength, and fatigue will eventually get it. Now, fatigue matters for ductile materials, right? For non-ductile materials like glass, stuff like that, we have to worry about fracture. So this, like I said, is ductile materials. Things that stretch. Steel does this. Most metals fatigue. What else? Plastics, things like that. Fracture mechanics are for brittle materials. Brittle materials like ceramics, glass, things like that. What we want to know is, when we have a fracture, how much does that flaw in it grow? How fast does it grow? Crack instability, right? How large does a crack have to get before it starts growing uncontrollably? How fast does it grow? A lot of research in materials now is somehow for brittle materials making it so that they don't fracture. They have great fracture characteristics, right? So like I said, we don't make stuff out of glass, despite the fact that glass's yield strength is much, much greater, like orders of magnitude greater than steel, because if there's a tiny little scratch in glass, that tiny little flaw in the glass, right, it creates a crack that then grows very fast, and you have failure of your part, right? So a lot of recent research into materials has been into how can we take these brittle materials and have them fracture in a sane way. And surprisingly, there's a lot of research, if you care to look into this, based on what's called biomimetics, right? Mimicking biological structures to improve our engineered structures. A good example of this is I don't know how to spell this. The conch shell. How do you spell conch? Well, I'll just try. You guys can look it up. Conch shell, right? Conch shell has layers and layers and layers of alternating layers of brittle calcium carbonate shell material, right? Layered with layers of proteins, adhesive proteins, right? So these proteins are very ductile, right? They deform under load with these very brittle calcium carbonate laminates do not deform under load. So what happens is you push on it, and the protein stops any crack that appears. If you have a crack, there's a good color. Yeah. If you have a crack that goes like this, suddenly it'll stop when it hits the protein because the protein just deforms instead of cracks. So it's a very, very robust way of making things. It's just very difficult to make if you don't have cells to do it. But we're working on it. All right, what else do we got? We got thermal properties. Right, thermal properties. Big thing is thermal expansion, right? What range of temperatures will your part experience, and how will that affect dimensions? If it gets too hot, is your part going to seize up simply because you've ate up all your tolerances? If you have fluids, you have to worry about melting / boiling, right? Under typical using conditions. You have to worry about what else? Thermal conductance, right? Conductance. If you're going to have heat generated in your device, you have to worry about where that heat's going to go, right? Conductance. Specific heat. Maybe you only have momentary sources of energy in your device, and you want to know, like, let's say you know that you're going to generate 150 joules of heat energy in one part. Well, if that part has a high specific heat, it can absorb all that energy without changing temperature very much. So maybe you want a high specific heat, maybe you want a low specific heat. Who knows? Also thermal stability, right? There are a lot of materials that are stable at room temperature that if you get them up to, say, 150 degrees Fahrenheit, all bets are off. Who knows what happens? They start outgassing dangerous material, like dangerous vapors, all kinds of terrible things. So thermal stability. This also affects the strength of a material, right? Let's say you make your device out of plastic. Perfectly strong enough at the range of environmental temperatures you would expect to see outside, right? So anywhere from 115 degrees Fahrenheit down to negative 20 degrees Fahrenheit. Wonderful strength. But you get that thing up to 140 degrees Fahrenheit, like you might see in the interior of a car outside in the middle of summer in Lubbock. Suddenly now it's so weak, it deforms and your part fails. So thermal stability. A big one, like we talked about, is manufacturability. I don't even know if that's a word, but I'm using it. Manufacturability. How available is your part? Is your material, right? There's a classic story of, I think it was the tungsten that they had to use at the SR-71 Blackbird, right? So that engine, because it's running at supersonic speeds, runs at these terrifically high temperatures. So you need materials. Maybe it's titanium. I can't remember. It's an exotic metal. And really, at the time, the only good source for this metal was the USSR, right? Our enemy at the time. This is the middle of the Cold War, right? We could make it in the U.S., but the quality was not high enough for use in these planes. So the CIA had to go through these crazy schemes just to acquire this titanium from the USSR, tungsten, so that the USSR didn't know that we were trying to build this crazy awesome spy plane. Right? So availability. Also, I should mention too, a big thing nowadays is something called lean manufacturing, right? And just-in-time manufacturing, where you're not only trying to not waste materials, but also try to make things as they come in. You're not trying to keep these large inventories, right? So can you get this material on short notice because you're trying to make these materials make these products on short notice. So, your processing ease, right? Processing ease. How easy is this thing to machine? Oops, that's not how you spell machine. How easy is this thing to machine? At one point, I was trying to make something for a research project out of stainless steel. I had these stainless steel washers, and I had to drill a hole in it. If you've ever worked with stainless steel, you know that stainless steel work hardens, right? Work hardens, which means it gets much, much harder under the kind of deformations that occur when you're trying to machine it. So I was trying to drill these holes in this, and I must have broken 5 or 6 drill bits, which really pissed off the machine shop guys. Work hardening. How easy is this thing to machine? How about weldability, right? Some materials are much, much easier to weld than others. Aluminum is much more difficult to weld than just plain steel, right? Moldability. How easy is it for you to just mold this part if it's plastic? Some plastics are much easier to just injection mold than others. Moldability. If you're trying to forge a part or cast a part, how well does it conform to the cast? How easy is it to cast? How much does it change shape while you're casting it, right? Because it's changed in temperature. Huge number of questions. Another thing you should consider is along manufacturing processing needs. Not only can you machine stuff, but with like sheet metal, you can punch it, you can fold it. If you can make something out of sheet metal, it is far preferable to machining it, welding it, or perhaps casting it's a little bit easier than using sheet metal. But anyway, so processing is how easy is this material to process? This is a large component, like I said, of your final product cost. So not only how cheap is the material itself, but how easy is it to make something out of it. And finally, you're going to want to worry about quality assurance, right? One of the fascinating things about wood is that it's not that terrible a material to make things out of. But it's very difficult to ensure that you have a good quality piece of wood, right? You have to actually have somebody look at it, and you have to kind of be an expert, and that is expensive. So, how consistent is the quality of your material? And finally, the last thing the last category. There's a mind-bogglingly large amount of things to worry about when you're choosing materials. Is hostile environments, right? Hostile environments. Moisture. How will moisture affect your product? I don't know how to put this. Organic stuff growing. We'll just call it stuff growing. How about that? Stuff growing, right? There's a lot of building materials that can withstand weather just fine, but you let vines grow on your house, and suddenly now it starts pulling your material apart. So stuff growing on it. How will it satisfy that? Temperature. How will temperature affect your product? We talked about how it'll make it weaker, but it can also make it more brittle, right? If it makes it more brittle, it might have worse fracture mechanics. Temperature. What are the temperatures your material will have to withstand? What about pH? How acidic or how basic will the environment be? Some materials are fine at neutral pHs, but you put them in an acid and suddenly they're gone, right? Salt environments. How salty will the environment be? Again, this is corrosion, all kinds of things. You have to worry about hydrogen sometimes. A little bit more esoteric, but a lot of metals, right, will absorb hydrogen into their crystal matrix, and it's crazy. The hydrogen just kind of wiggles its way in, and it really makes it much more brittle, right? Which, one of the huge advantages of metal is that it's ductile, right? When it fails, it doesn't fail, it doesn't fractures. It bends, so you have time to get out of that car before it just crashes. Well, that was a terrible example, but you get the idea. Hydrogen. Galvanic reactions, right? You put two dissimilar metals touching each other, and what do you got? You got a battery. But you only have a battery if you put a conductor in between them, a conductive ionic solution. So you need a salty solution with moisture in the environment, right? You know, I've seen products where they didn't consider this. They put I can't remember what the two materials were now. I think it was what was it? Well, it was some kind of sheet metal with steel rivets. I can't remember if it was aluminum and steel. Maybe it was aluminum and steel. In any case, it corroded the aluminum, so that these rivets just ate right through the aluminum because it formed a battery, and that battery just it's got a closed loop, right? You have two metals in contact. It's not like you have an open switch in between them, so it just runs until it consumes all of its material, which is the metal itself. Galvanic reactions are terrible. What else? You might have to worry about magnetic fields, right? Is your material paramagnetic? Will it respond to magnetic fields? Electric fields. If you're in the presence of alternating electric fields, if you have a conductive material, it'll generate currents. Those currents might heat the material up. All kinds of bad things happen. We could go on and on and on. Your task, should you choose to accept it, your task as an engineer is to recognize which of these things, and others, right? This is not a complete list. Which of these things is important for your design problem? That is not a trivial task, because it requires you to imagine how your product is going to be used, imagine the environments it's going to be in, right? This galvanic reaction thing requires experience, right? You have to know. Look, two dissimilar metals in contact, you're going to accelerate the corrosion that might occur normally. Ironically, you can also use galvanic reactions to protect materials. So the steel pipelines that they have running from like Alaska all the way down to the continental United States, every couple hundred yards, they'll plant a large chunk of magnesium in the ground. And it's called a sacrificial anode. If you're big into boating, sometimes they'll have is it copper? I think it's a copper plate that they'll just attach to the bottom of the boat in the water, and they'll connect it electrically to all the other metal parts in the boat. And the idea is that if one of the material is going to corrode, the sacrificial anode corrodes first. So instead of the steel pipe corroding, the magnesium block corrodes and your pipeline stays secure. And in the case of the boat, that copper plate corrodes instead of your really expensive outboard motor, right? Awesome. So you need to recognize what's important for your design problem. And once you have once you've identified the important properties for your material, then we need to develop. Ideally, we need to develop models to help us recognize important parameters, or how our system behaves. This is becoming increasingly difficult, largely because computer-aided design, we forego these analytical models in lieu of just a computer model, right? And we hopefully just churn out lots of different results from our computer models. So we make a 3D CAD drawing, and we throw it into ANSYS or some FEA program to give us the results. But let's just do a quick example of how a model might work. So if we look at a simply supported circular beam, I know you guys are having flashbacks to your solid mechanics class now. So simply supported P with some diameter D. We know that the maximum deflection of this beam, delta, is equal to the load times the length cubed divided by 48 times the modulus of elasticity times the moment of inertia of the cross-section of that beam. So for a circular beam, this is equal to PL cubed over 48 E pi d to the fourth over 64. Yeah. This is just a demonstration. Obviously, you don't have to remember how to do this, but awesome. So we know the weight depends on the diameter. So let's say for this product, we know that it needs to support a certain support a certain load P without deflecting too much, right? Without deflecting too much, that deflection is delta. So the important parameters for this thing that we're trying to optimize are the deflection under a load P and the weight of our beam. Okay? So the weight is given by, W is given by the volume of that beam times its density, which is just equal to the length times pi d to the fourth divided by 4 times the density. We can solve this for the diameter, and set them equal to each other. And then we can solve for the weight. And what do we get? We get that the weight of this object is equal to pi over 2 times 3 pi to the 1/2 times, I'm not doing this all in my head. I have this written out earlier. It'd be awesome if I did, though. 5/2 times the load divided by the deflection to the 1/2, and the density divided by the modulus of elasticity to the 1/2, right? So we know that we want to minimize our weight, right? We want our weight to go down. So that means we want to minimize this entire quantity here. So for a given stiffness, right? Our stiffness of any object is defined as the load divided by the deflection. For a given stiffness of this geometry in this beam, we know that if we want to minimize the weight, we have to minimize the density divided by the modulus of elasticity to the 1/2. This is a parameter that we want to minimize. Okay? So, what extra information did we get from doing this, right? We got that we knew that if we wanted to minimize the weight, we had to minimize the density, right? That's obvious. But what we learned is that the parameter that really matters is the density divided by the modulus of elasticity to the 1/2. Okay? Which is pretty great. So how would we use something like this? What we're going to do is we're going to use in this class something called a weighted normalized decision matrix, right? We've talked about decision matrices before. Earlier, when we were choosing between our concepts, these are not equal. We talked about a Pew decision matrix, right? A Pew decision matrix is used when you have incomplete information, right? You don't know, you're just using conceptual designs. You haven't done any analysis, you don't have any numbers. So that's when you use a Pew decision matrix. When you have numbers, but they're difficult numbers to compare, right? We're not just comparing the weight of 3 objects. We're comparing a whole suite of different things. We're going to use a weighted normalized decision matrix. I'll describe it. So along the left-hand side, you're going to put your different options, right? In our case, these options are different materials. So we'll have maybe steel, aluminum, and titanium. These are materials. Along this direction, we're going to have different properties that we have decided are important. Okay? So these different properties might be the yield strength divided by the density. It might be the modulus of elasticity divided by the density, and it might be the cost times the density divided by the yield strength, right? And we found these the same way we found that the density is divided by the modulus of elasticity, the 1/2 was important for our simply supported beam, right? We develop a model, and then we do what we can to simplify it to find important parameters that are only dependent on the materials, right? We don't care about the length. That's not a material property here. Pi is obviously not a material property. And when we solve for this, remember we solved for everything in terms of diameter and then set them equal. So we got rid of the diameter. Again, not a material property. We were looking for material properties that affect things that we care about, like the weight. Awesome. So for each of these properties, looks like I have to do a little adjusting here. Let's just do that. Move this down here. So for each of these properties, we're going to have to determine a weight. A weight. Here I'm going to list them as A, B, and C. And we're going to have to determine, so we figured out a weight. This is how important each object is, right? It doesn't matter how you choose it. It could be 1 to 10, it could be 1 to 100, it could be 1 to 1,000, it could be 0 to 1. It doesn't matter as long as you're consistent, right? Give them a weight. How important are they? And then for each of these, for these properties, we're going to figure out what the value for each of these things is, right? So in this case, we'll actually use real numbers. I'm going to choose my weighting to be 2 for A. For B, the weighting is going to be 1. Oops. And then for C, we're going to have our weighting equal to 3. Okay? All right. Okay. Now, again, whether or not these are important is dependent on the geometry of the part, the type of the load. It's going to be different for every problem. So these are not the parameters, these properties you are going to use for your own problem. In fact, you might have to come up with different properties, like just plain the cost divided by the density. Who knows? So for each of these things, you're going to write down the actual value. A stands for actual. So, for example, in this case, steel, the yield strength divided by the density for steel comes out to 221. For aluminum, it comes out to 148. For titanium it comes out to 241, right? So what does this tell us? It tells us that titanium has a larger yield strength to density ratio than steel. This is why people use titanium, right? Well, and it's corrosion resistant. But it's stronger for per unit weight than steel is. Now we're going to turn these into relative values. So we're going to take each of these values and divide it by the largest one in the column. So let's start with titanium. Titanium is 241 divided by 241, so its relative value is 1. Aluminum is 148 divided by 241, so its relative value is 0.61. And steel is 221 divided by 241. Its relative value is 0.91, right? Fascinating that titanium is only about 10% better than steel, which is why oftentimes people will just use steel, unless the corrosion resistance is, like I said, important too. Awesome. So, now let's look at the modulus of elasticity divided by the density. So this is a measure of the stiffness to weight ratio, right? So for steel, the value that we get is 26. Ironically, for aluminum, we get the same value, 26. And for titanium, we get that it is 27. So, and you will look up these properties, by the way. The yield strength, the density, all of these materials, you can find these in tables everywhere on the internet, or in handbooks of materials that you can get from the library. So for steel now, we have to do the relative value. So we take the largest value in largest actual value and divide all the actual values by that largest value. So we have 27 divided by 27 is 1.0. 26 divided by 27 is 0.96 and 0.96. So what's cool about taking the relative value, right, is we've taken these things, like this column here is in the hundreds, right? This column is in the tens. How would we normally compare these? It would be very difficult, right? Well, if we take the relative value now, it's very clear. It doesn't matter that this one's an order of magnitude larger than this column. Now we just care how much better or worse is each thing than the best. All right, now for the last column, we have 2.9, 4.7, and 20.5. This tells us roughly, right, this is roughly how much cost per yield strength we get. So we find out that steel is very cost effective, titanium is not, right? You have a lot of dollars for the same yield strength. So again, we have to make the relative value here. So we take the highest value, again, which is titanium. So this becomes, not 2, but 1.0. 4.7 divided by 20.5 is given by 0.23. And 2.9 divided by 20.5 is 0.14. Oh, I gotta wait while this is saving. Okay, 0.14. Now we need to combine all these things in a way that makes sense. We're going to use a weighted average. Okay, a weighted average. So, it also depends, this weighted average is going to depend somewhat on whether or not we want to maximize. We want to maximize our yield strength. We want to maximize our stiffness. But we want to minimize our cost, right? So the way we're going to construct this is we're going to take our weight, A, multiply it by, call this R1, R2, and R3. So if we want to maximize something, we're just going to take the weight and multiply it by the relative value, R1. And we're going to add it to all the other things we want to maximize. So B times R2. If we want to minimize something, right, what we're going to do is we're going to take its weighted weight, in this case C, and multiply that by 1 minus its R value. Okay? It's as simple as that. So this is what happens when we want to minimize something. This is what happens when we want to maximize it. Now, this wouldn't be a weighted average unless we divide by all of the weights. A plus B plus C. Okay? This will give us a number between 0 and 1 for each of these values. So if we do this, we're going to take 0.91 times 2 plus 0.96 times 1 plus 1 minus 0.14 times 3. And that gives us a value of 0.89. Aluminum has a value of 0.61 times 2, 0.96 times 1, and 0.23 times 3 times 1 minus 0.23, which gives us a value of 0.74. And finally, for titanium, we take 1 times 2 plus 1 times 1 plus 1 minus 1, which is 0, times 3, which gives us a total value of 0.5. In each of these cases, remember, we divide by the total of the weights. So the total weight is 6, right? Great. So what do we find out? We find out that steel is the winner, right? Why did steel win, right? Steel lost in terms of our strength to weight ratio. It lost in terms of our stiffness, right? But where did it win? Oh, it won big in terms of cost, right? Steel might have lost if we had changed our weightings, right? If we change our weightings and made A, let's change our color here. If we made A have a weight of 10, our strength to weight ratio and our stiffness to weight ratio have a weight of 5, let's say, and our cost have a weight of 1. This is a case that might happen if you're working for the military designing a fighter jet, right? They don't care what the cost is. They just want that strength to weight ratio to be as high as possible. They want a high-performing machine at any cost. In that case, you might find that the titanium wins. But in our case, which is a realistic, where you're selling on an open marketplace and not just bidding for government contracts, so cost matters, we have a winner of 0.89. This isn't the only consideration you would make, right? You're also going to have to worry about manufacturing. It's hard to quantify manufacturing, right? You're going to have to worry about corrosion resistance. In these cases, if you're unable to form a model and to use a weighted decision matrix, which really only works when you have these quantitative values, right? Then what would you use? You'd use a Pew decision matrix. The point is to use some kind of decision matrix to help you choose what material you have. To narrow it down to a range of options and then use a decision matrix to pick a winner, right? And remember, if we use a Pew decision matrix, we have to pick a datum. We have to do it twice to make sure we didn't make any mistakes. So if you're going to use a Pew decision matrix, make sure you use it correctly. Let's worry about corrosion resistance, fatigue. Material choice is not a trivial matter. In fact, we could spend an entire semester just talking about material choice. We only have a week, and you have other stuff to do. So, all right, that's it for now for material choice. With your assignment, right, what I want you to do is take two important parts, not non-trivial ones. Don't just pick two screws. Pick two important parts and systematically choose the material for them, right? That might mean making a model and using a weighted decision matrix. That might mean talking about manufacturing and corrosion resistance, fatigue, and using these as your parameters in a Pew decision matrix, right? But you need to be systematic about it. If you have any questions, come talk to me in class, and we can figure out the best parameters and the best way for you to do this. But I need you to do this for two important parts. And I'm also going to need a list of all of the parts in your product and preliminary material choices. So for two parts, I need a full workup I need some kind of description of their decision process. For all of the other parts, I need you to just choose a material. Okay, you don't need to give me reasons for choosing it. As time goes on, we can develop reasons for choosing them, and maybe have to change. Well, obviously, we'll have to change the choices that you make. But for now, I just want you to list all of the parts in your product and a preliminary material choice.